What's up, YouTube fans? What I wanted to talk about in this video, right, is one of my favorite like biological systems, if you will, to show the evolutionary reducibility, evolutionary steps of would be the locomotion, right, of various creatures, including humans, right? So locomotion refers to like the way something moves around, right? So like the various ways which creatures move around from place to place, right? There are some living things which just stay in place pretty much just about their whole life, right? Like a tree. I've got a tree outside there, it just stays in place, right? But us humans, we walk all around from place to place to place. It's obviously very complex. How did that get started? How do we go from eventually tracing back to things that didn't really they virtually had no movement, to things that move around like how we do? Can it be broken down into a series of evolutionary steps, each useful in its own right? Yes, it can. So I'm gonna be strictly focusing on like changes with like the skeleton and the muscles, etc., that help with movement. Not other parts of the skeleton that are not like essential towards moving around, right? Like the jaws, that's separate. Doesn't have to do with how we move around. But so first off, humans, right, obviously transition towards moving bipedally more, right? A large amount of the unique features of the human skeleton, which differ from that of other great apes like chimpanzees, a large amount of these differences are all centered around one thing: bipedalism, right? Meaning the ability to move on 2 feet. A significant amount of the unique features of our skeleton are all features which make us better at moving on 2 feet than a chimpanzee is, right? But the ability to move on 2 feet like how a human does, that's obviously not irreducibly complex, because all apes alive today move bipedally to some extent. It's just that none of the rest of them from us are as good at it, right? But they still are better at it than most mammals, right? So like better than a dog is at it. And they can move significant distances bipedally. Recently, for my birthday a few weeks ago, me and my mom and dad went to the Lincoln Park Zoo. And at one point, one of the gorillas, he like got up on 2 feet, or I don't know if it was a male or female, but it got up on 2 feet, and they were like outside, right? It got up on 2 feet and it like strutted in, walked in the door like a human, right? And it did pretty good at moving bipedally. Like it didn't seem like it was like stumbling or anything. It just like strutted on in. So you will see them do that sometimes. They don't move bipedally as much as us, right? Any other apes alive today do not move bipedally as much as we do, and they're not as skilled at it as we are, but they still can do it, right? So there's a gradient. Something need not be as good at moving bipedally as the modern human is to be capable of moving bipedally, right? And creatures that do move bipedally, right, will get advantage from, various, variants which make the individual better at moving bipedally, right? For creatures that do move bipedally, those individuals, right, you could see how they would they could get advantage in successfully producing offspring, right? Because then they're less likely to like trip and fall if a predator is chasing them or whatever. um and as for like the original reason for transitioning to moving bipedally, like more often, there's differing advantages, like being able to carry more things like food, carrying babies, carrying tools. um some have suggested that it might be more metabolically, or I mean less metabolically costly of a way of moving around when on the ground. And And so, in any event, there's a gradient. Something need not be as good at it as humans, to be able to move bipedally at all. And so long as a creature gets any type of like the species gets like a significant advantage from moving bipedally more, where individuals that are better at moving bipedally have higher statistical odds of producing offspring, right? Then we can expect for over time variants that are better at moving bipedally to persist more. And some of the factors as to like why was it advantageous in our ancestry, some of that is not really predictable. It's up to like chance environmental factors. um it's not like a predictable type of thing that it like has to happen that way, which is why we don't see that it didn't happen that same way in any other apes, like group of apes, right, that we know of. um and so it doesn't have to be like a predictable thing that like, oh, anything that's an ape has to evolve that way. It's up to a lot of chance environmental factors. But it doesn't have to be like a coincidence that like, oh, why do we simultaneously have so many features at once that are good towards like that make us better at moving bipedally. Because once our ancestors already were, obviously it's going to be better for them to be better at moving bipedally. And so long as they are getting a significant advantage from moving bipedally for whatever reason, this reason or that reason, then variants that make individuals better at it can be expected to persist across generations. And most of the changes involved with making something like better at moving bipedally than a chimpanzee, most of the changes that make us better at moving bipedally than a chimpanzee is, the majority of these are not like matters of like, oh, we have this body part and they don't even have it at all. It's mostly the same parts, just modified in different ways. So it mostly doesn't involve like evolving any totally new parts, but mostly just tweaking already existing parts, right? Like our legs and feet, our pelvis, our backbone, all of these things have the same fundamental structure as that of a chimpanzee. It's most of the same fundamental structure, but modified in different ways, right? And so, well, and also worth noting is like, it's not like any like individual that's already fully formed that like, oh, their foot is just going to be like modified to be different. It's the genetic instructions that are modified. And so then when a new individual develops in the womb, and then when they're out of the womb, when they grow and develop, the way that it forms is different, right? Some variants will help the individuals, right, with that variant to be more likely to successfully produce offspring, right? As creatures, out in the wild compete for their survival, compete to successfully produce offspring. And so, that's basically the summary on like the transition, right? The transition from, something that is not as good at moving bipedally, has a skeleton more like that of a chimp, to something that's as good at moving bipedally as a human. Also, another change of locomotion that happened in our lineage is that we started not climbing trees as much, right? That's that's less complicated because it's mostly just a loss of function. Just like our shoulder blades are not as tall as a chimpanzee. Various changes make us not as good at tree climbing, partly because some of the features which help with tree climbing, we gave those up in favor of bipedalism, right? So, like, for example, the type of feet a chimp has are better for tree climbing than our feet because they have grasping ability of the feet. For us, our feet no longer have grasping ability, so are no longer as good for tree climbing. But the way that our feet are, with the big toe lined with the other toes, that is better for bipedal movement, right? Meaning moving on 2 feet, right? And so, it eventually leads back then to creatures that were not as skilled in moving bipedally, but still could move bipedally and spent a lot of time in the trees, likely move quadrupedally sometimes on the ground, possibly already were moving bipedal on the ground a lot, even the last common ancestor with us and chimps. In the case of gibbons, that's the second most bipedal primate of living primates after humans, and they're also apes. They're one of the apes, and they so closely related to us within the primates, and they spend most of their time on the trees, right? But when they are on the ground, a very large percentage of their movement is bipedal, right? Moving on 2 feet, and they basically run on 2 feet, right? With like their arms like splayed out to the side, like like this, like they like run like with their like arms like splayed out to the side. They like run like that, right? And so, possibly, the last common ancestor between us and chimps might have been more like that, or maybe it moved more like orangutans. We don't really know exactly the way it moved. But in any event, the ancestors of all apes, right, the last common ancestor of all apes, evolved a feature which is unique to, it's one of the features that distinguishes apes from other primates like the old world monkeys. Humans still have this feature, a dorsally positioned scapula, right, allowing for highly mobile shoulders, right? This is one of the major features that distinguish apes from old world monkeys, along with not having a tail, and the Y5 molar pattern. Us humans have these features too. They're the major features used to distinguish between old world monkeys versus apes. Apes also lost the tail, right? The ancestors of all the apes. So that's when our ancestors started not having a tail, is in early apes. And that is also somewhat indicative of a change of locomotion, because for creatures that do have a tail, it helps with their form of locomotion, right? But apes do not have tails, partly because of having a more upright posture that more so allows for moving bipedally. Apes therefore no longer require a tail so much, right? So in apes, the tail was lost, right? And so all apes have no tail, right? Gibbons, orangutans, gorillas, chimps, bonobos, and humans, we all have no tail. That's why you don't have a tail, because you're an ape, right? And so in any event, then tracing back to the earliest primates, right, the ancestors of all living primates, the last common ancestral species to all primates, they were beginning to spend more time in the trees, just as most primate groups do. We're not the only ones that no longer do. You know, there's some baboons, I think, and, you know, a few other groups of primates that, you know, no longer spend most of their time in the trees, spend most of their time on the ground like humans, right? But most primates do spend most of their time in the trees. All primates have inherited various features that help with climbing in the trees, and there's various evolutionary advantages that some species could get from spending more time in the trees, like, you know, it could help with avoiding predators on the ground if the predator is not itself as good at tree climbing or even able to tree climb. And so then if it's chasing you and there's a tree there, you could climb up the tree and then it can't eat you anymore. So that could give a significant survival advantage. The individual is then better at tree climbing, more likely to survive, by extension, more likely to successfully produce offspring, right? Also, another significant advantage, trees have things in them like fruits, right? Things that you can eat, right? Mostly fruits, you know, sometimes other animals that you might want to prey on if there's another animal that tree climbs. Mostly fruits, right? That would be the main thing to eat in the trees. And so climbing in the trees could also give that survival advantage, right? And so for some species, they could get significant advantage from spending more time in the trees, right? And so then any features which, you know, help with climbing in the trees, right, could make the individuals with that variant more likely to successfully produce offspring, because, you know, then they're less likely to fall out of the tree to their death, you know, more likely to, you know, quickly escape a predator when climbing up the tree, more likely to reach fruits that are on far out branches, etc., many advantages, right? And so it would seem that the ancestors of all primates evolved several adaptations to life in the trees. Is very evident that that is the case, because most primates do spend a lot of time in the trees and have several features which all help with life in the trees, right? And so some of these include, you know, a post-orbital bar, right, where there's bone around the eyes. That's one of the major traits of primates, is to have forward-facing eyes enclosed by bone. The skull does not have to be like that. There's plenty of other creatures where it's not like that. For most mammals, it's not like that. Why is it like that for us? Because we are primates. Early primates modified what was the claws into nails, right? So most mammals, they have claws, but primates, including humans, have nails, which are different from claws in that they're shorter and flatter and wider, right? So see here on my thumb, that's a nail, very much like what you will see on a gorilla's thumb, right? But not on a dog, not on most mammals. And then also, as primates transition to life in the trees, spending more time in the trees, they modified the limbs such that the feet have more grasping ability and the limbs were more mobile. And in doing so, what was the front legs and feet became modified into arms and hands, right? So what's now our arms and hands was originally a front pair of legs and feet, right? So even though different groups have become specialized in different ways, for most tetrapods, for most mammals, or well, I don't know that I should say most tetrapods, but it's more common than for a creature to have arms and hands that that amongst tetrapods that they would have a front, legs, and feet, right? And creatures that have 4 legs and 4 feet, many of them can still tree climb, right? Like lions, they have 4 legs, 4 feet. They can still climb high up into the trees, right? Same with lizards, some rodents. So a creature need not have arms and hands and need not be as good at tree climbing as a primate is in order to tree climb at all, right? And what we see in tetrapods is that regardless of the differing functions that tetrapods use their limbs for, most tetrapods have exactly 4 limbs, right? But for many, like dogs, rather than having arms and hands, they have a front pair of legs and feet. But the front legs and feet of a dog, it's the same fundamental structure as your arms and hands, all of the same bones: humerus, radius, ulna, carpals, metacarpals, and digits with phalanges. Digits is what we call fingers or toes, right? The fingers and the toes have the same fundamental structure, right? And most commonly we see in tetrapods for it to be exactly 5 digits per limb, regardless of the function that they're used for. That is the most common within tetrapods, right? And so the evolution of the arms and hands, it's just a matter of modifying what was the front legs and feet into arms and hands through the process of evolution by natural selection, adaptation, right? Through means of adaptation as creatures adapt to life in the trees, what was the front legs and feet became modified into arms and hands, right? And so then tracing back to creatures with a more generic mammalian skeleton, right? And then next, the ancestors of all the mammals evolved a unique skeletal trait that we tend to see in mammals, where the legs are more vertically positioned, right? So like the legs come out more so under the body, right? Whereas what we see commonly in like reptiles and in like salamanders, what we commonly see in like a lot of other groups aside from mammals, other tetrapods, is their legs come out more horizontally. So it more so looks like that they're like crawling across the floor. Unlike a dog or an elephant that, has its legs under the body, the lizards, crocodiles, salamanders, what we see in them is that their legs come out more so out of the side of their body, right? And so that's a less advanced form of movement, the type of movement that we see in the earliest tetrapods, right? But in mammals, it becomes more advanced where the legs are more so positioned under the body, right? So more so specialized towards terrestrial movement, meaning movement on land, right? Whereas the more primitive setup is like what we see in lizards, crocodiles, salamanders, where the legs more so come out of the sides of the body, and it more so looks like that they're like crawling across the floor. And then this takes us back to the earliest tetrapods and the transition from creatures that spend all of their time swimming around in the water to creatures that walk around on land. So first off, the earliest tetrapods spent a lot of time both in water and on land, right? Early amniotes, which is a group we're a part of, lost their gills, likely became fully terrestrial, not spending any time on land, right? but the earliest tetrapods had gills, spent a lot of time both walking on land, but also a lot of time in the water swimming around, which is also what we still see commonly in amphibians, right? Which is the first group of tetrapods for us to branch off from after the early tetrapods, right? So in any event, the transition to life on land, what you'll want to understand, right, is something need not be as good at moving around on land as like a salamander is, as tetrapods are. Something need not be as good as that at moving around on land in order to move around on land at all. There are even some fish still alive today which can move around on land and spend extended periods of time on land. You know, the DNA evidence indicates that the closest living relatives to tetrapods are the lungfish, and they have two pairs of fins which are modified into primitive limbs, right? So even though they're fish, they have primitive limbs which are also fins, but unlike the fins of most fish, the muscles which move the fins are not just simply at the base of the fin, but also within the fins themselves, right? And they have a similar bone pattern in their fin limbs, which it's similar to the beginning part of the limbs of tetrapods, right? With one big bone followed by two smaller bones, right? And they can spend significant amount of time on land. They also have lungs, right? Unlike most fish, they have both gills and lungs, right? And so even though they're fish, they can spend a significant amount of time moving around on land, right? Extended periods of time, even days on land. They can go a whole day out of the water, even though they're fish. And they can move around on the land. They do it frequently, right? There's also another group of fish which evolved in this way independently called the mud skippers. And even though they're fish, they actually spend more time on land than in the water, right? So they're able to move around on land and they spend more time on land than in the water, right? So even though we traditionally think of fish as creatures that swim around in the water, and that almost seems as though that it's like a defining feature of fish, something can actually be a fish and move around on land, right? And so something need not be anywhere near as good at moving on land as a tetrapod is to be able to move around on land at all. And there are evolutionary advantages for creatures that already move on land some to begin spending more time moving on land, such as, for one thing, it can help with avoiding predators that are in the water. If there's a predator that itself doesn't ever go on land, it could be an easy way to escape it when it's chasing you to go onto the land, right? Also, accessing resources on land like food, right? And then also in the case of escaping predators, what you'll also want to note is, that wouldn't as much work now in the present because there's a lot more animals that have colonized the land by this point. But in the time period of when the first tetrapods were colonizing the land, there was much less like predators on the land that would be problematic for them, right? And so you have to understand that context also. And also, some things which give us insight of the evolution of the tetrapod limbs, certain mutations give us insight on that, right? Like there's some individuals, even for us humans, they can be born with 6 fully formed, fully functional fingers on a single hand, right? And that's an inheritable trait that can be passed on from parent to offspring, right? So what this shows us then is most of the same genetic instructions are used for one finger to the next, right? And so it doesn't have to all be evolved from scratch for every single finger independently. That's not how it works, right? Also, we know from we know that most animals, including humans, have body segmentation where our body is divided into a series of segments. And there's this thing called the Hox genetic code, which works in conjunction with the segmentation, where basically the segments help with like determining the positioning of differing parts across the axis of the body, and then certain body parts can be placed repeatedly across that axis, right? And this goes way back in evolution, way before the evolution of limbs, all the way back to our last common ancestor with like insects. That's how far we're talking, like even before our ancestors were fish, way back. That's how far back this goes. It's found in almost all living animals. And so various features like the vertebrae, the ribs, it doesn't have to be evolved from scratch for each individual one, because body segmentation in the Hox genetic code, this allows for the same parts to be placed repeatedly across the body's axis. And so this also applies to the limbs, with the front limbs and the back limbs of tetrapods, that it does not have to be evolved independently from scratch, right? And then also bilateral symmetry, right? Which also goes way back. The fact that we have, the left side of our skeleton mirrors the right side. It's mostly the same structure from left to right. And so the left parts do not have to be totally evolved independently from scratch from the right parts. It's mostly the same parts, and so it evolves in conjunction. It doesn't have to be evolved independently, separately. And so the left and right limbs, the front and back ones, it doesn't have to all be evolved independently. Most of the same genetic instructions can be used, and also for each of the digits, right? And then also worth noting is that in early tetrapods, they likely had webbing between the toes, which we still see in many living tetrapods, like a lot of amphibians, right, where it's filled in with skin and muscle between each of the digits, right? The toes, it was all toes in the earliest tetrapods. Now it's fingers for us for the front ones. And so that can be the early setup for tetrapods. It most likely was only later, as a later modification, that there's space between the fingers and toes, as we see in most mammals. And it still is the case that actually that during embryonic development, when us humans first form our fingers and toes, it still is filled in like that, right, with skin and muscle between, right? And in some cases, it fails to like have the space develop. And so a person can actually still be born like that. There's still a condition where a person can be born with it filled in like that, like a frog, right? And so that is likely the condition of the earliest part, like the earliest limbs of tetrapods. Some still retain that. Some have even re-evolved it, because the instructions for building it that way are still there, as I already explained, right? And so this breaks down step by step the evolution of our limbs. Then also, earliest sarcopterygians, so this is tetrapods and lungfish and coelacanths, which the lungfish and coelacanths, they have primitive limbs, right, where two of their pairs of fins are primitive limbs, with the beginning part of the tetrapod limbs is like the beginning part of it is similar to the beginning part of the tetrapod limbs, right? This shows that in the earliest sarcopterygians, right, which includes tetrapods, lungfish, and coelacanths, the earliest sarcopterygians were already adapting some to life on land, right, eventually leading back to more generic fish, right? And so then creatures that, spent most, if not all, of their time in the water, even more generic fish can go on land sometimes and move around on land. Some of them can, right? Like catfish can be observed, waddling across the land in some instances, right? Um, but so eventually leading back to the earliest tetrapods, which spent all of their time swimming, but they had fins, right? Not limbs, but they had fins, right? And the earliest tetrapods, the fins only had cartilage, no bone. This is what we still see in the most primitive living vertebrates, like the lampreys, hagfish, sharks, rays, chimeras. They still have skeletons entirely made of cartilage with no bone. Later, the osteichthyes, which is a group most living vertebrates, including us, are a part of, they modify the skeleton such that it's made out of bones, not just cartilage, right? And so then the earliest vertebrates evolve fins, right? Which this improves their locomotion, but it's not necessary for a creature to be able to swim around in the water or even to be bilaterally symmetrical. Flatworms, for example, they swim around in the water, but there's no fins. At least I'm pretty sure they don't have fins. Even if not, there's other examples. Jellyfish, they don't have fins. So creatures can not have fins, but still be able to swim around in the water. And then the earliest bilaterians, which is a group including the vast majority of living animals, they evolved bilateral symmetry, body segmentation, the Hox genetic code, many of these various features which played a role in their locomotion, right, but were not necessary for it, eventually leading back to the earliest eumetazoans, right, which likely moved around more like comb jellies or jellyfish, right? And then in the very earliest, like primitive, like beginning of movement, beginning of like the evolution of locomotion from creatures that basically didn't move around at all, like a sponge, how does that get going? Well, what helped a lot is that it started in the water, right? And so the water current naturally drifts things around anyways, even things that are not living, right? Non-living things in the water will often just drift around. And so the earliest locomotion could be started without any effort on the part of the individual, the individual organism. The water just drifts them around. And so then, because they don't really even need any effort to move at all in the water, then small tweaks can improve upon that. Just like basic contracting in the water can make a difference in, how much they can move, just basic ability to contract, right? And then it improves from there, more and more specialized, right? And so eventually leading back to things that make no effort at all in moving, right? And so from that all the way up to us, right? That's the whole thing broken down to the start. And so, and by the way, so I was a little bit second guessing myself with saying that jellyfish and flatworms don't have fins, because if I don't remember if maybe they have something that's called fins, but I'm sure there are some things that move around without anything called fins. They certainly don't have fins that are the same as vertebrate fins, regardless of the, the points still stand regardless. So in any event, all right, that's all for now. See you guys.